Homework 14, Rational Functions, Video 5. Graphing rational functions using the 7-step process. Not sure why functions has 2 T's there. Example 2. In the previous video, I naively said, let's do this one because I used it as examples earlier, and it got a little bit crazy, especially in the middle there. And I probably should have started with a simpler one like this. And when I say simpler, I mean first degree polynomials on either side. Graph f of x equals 6x over x minus 3. I'm not going to rewrite all the steps, but I will go through them. Step number 1 is to see if it's odd, even, or neither. I will save us some time and tell you that this is neither even nor odd. You can check it by plugging in a negative x and comparing it to the original and the opposite of the original, but neither one of them will match. Let's find the vertical asymptote, and we'll be pretty quick about it. For the vertical asymptote, you start by looking in the bottom and solving it equal to 0. If I solve x minus 3 equals 0, I get x equals 3. Does that make the top equal to 0? No. If I put 3 on the top, I get 6 times 3, which is 18, but it's not 0. So x equals 3 is a vertical asymptote. This graph has no holes. For the horizontal asymptote, we compare the degrees. As I already mentioned, both sides of these have degree 1. And when the degrees match, the horizontal asymptote is y equals the ratio of the leading coefficients. The leading coefficient on the top is 6. The leading coefficient on the front of the denominator is 1. So we have a horizontal asymptote of y equals 6. So pretty straightforward. For the x-intercept, you solve the function equal to 0, but you basically just solve the top equal to 0, because the only way a fraction can be 0 is if the top is 0. There's the rare case where whatever makes the top 0 makes the bottom equal to 0, and that would create a hole in the graph. I guess you could say a hole in the graph is also a number that is trying to be both an x-intercept and a vertical asymptote at the same time. But if we solve 6x equals to 0, that just gives us x equals 0, which is at the origin. So this graph will go to the origin. For the y-intercept, we just put 0 in, but that will give us 0 on top of negative 3, which is still 0. So our y-intercept is y equals 0. So the only intercept this has is at the origin. Let's sketch what we know so far and show you how you can really take advantage of what you know and what you don't know. Our vertical asymptote is x equals 3, so let's go over 3 and drop a vertical. Our horizontal asymptote is at y equals 6. So we'll go up 6 and shoot a horizontal asymptote there. Both intercepts happen to be the origin. This is all I know. But based on this and this alone, I know what the graph looks like. Because I know that it has to approach the horizontal asymptote on either end. I know that when it hits the vertical, it's got to go up or down. And I know I've got to go through this point. Pretty sure this is going to go down and then upwards towards the horizontal. We have this boomerang down here. There's absolutely no evidence over here, but I'm expecting another boomerang. And frankly, I'm expecting it up here. Why? What would happen if it were down here? It would have to have an x-intercept, and there isn't one. Now, you can speculate like that, and you might be right, but this is why I advocate finding other points, especially when you're not given them. But the trick for finding other points is to work around the x's that you know about. You will always know about x equals 0, because either that's where your y-intercept will be, or there will already be a vertical asymptote there. And we know what happens at x equals 3. There's a vertical asymptote. So I need x's around in between these. I need an x to the left of 0. Let's try negative 1. I just need some evidence. I don't need a lot. I need something between 0 and 3. So how about 1? And I need something to the right of 3. So how about 4? So let's just plug these 3 numbers into the function and see what happens. F of negative 1 will give me negative 6 on top. Negative 1 minus 3 is negative 4. That reduces and divides all the way down to 1.5. So when I go back 1, I go up 1.5. So about here. This confirms my suspicion that this graph's going to go up towards the horizontal asymptote. Let's put in 1. That gives me 6 on top, -2 on the bottom. 6 divided by -2 is -3. Meaning, when I go over 1, I go down 3. Further evidence that this graph is going to plummet as it approaches the vertical asymptote. If we plug in 4, we will get 24 on the top. It's kind of a big number. 1 on the bottom. Oh, goody. Over 4 is up 24. I don't have enough room for that. But I know there's a dot way up there. Let's get a little bit more evidence to the right of 3. Let's put in 6 and let's put in 8. Why 6 and 8? Why not? I could have used 5 and 6 or 5 and 7. If I put in 6, I'll get 6 times 6 is 36 on top. 6 minus 3 is 3 on the bottom. That's 12. So if we go over 6, I'm supposed to go up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, up here somewhere. See how accurate I'm being. I just need evidence, not down on accuracy. If I plug in 8, 6 times 8 is 48. That's kind of a large number, but 8 minus 3 is 5, and 48 divided by 5 is 9.6. So over 8 and up, not as high as this dot. All right, I've got the evidence that I need. These points over here confirm what I suspected earlier about this boomerang looking like that. These points up here, I really didn't leave a lot of room for it, but this graph would continue upwards towards the vertical asymptote. So these problems can be pretty quick depending upon how fast it is to find all the evidence and how quickly you can calculate the other points and then just connect the dots. I do want to take a look at one more that has an unexpected twist. And yes, there's one like it in your homework.